Welcome back after the break for this second part of the third lecture. We start again from the main inequality of the lemma we are proving, and here we emphasize the content of remark remark 1 we proved just before the break, and we also emphasize that the Cauchy-Schwarz inequality in the remark number 1 was made in a way such that there is this cancellation of terms. Now we move forward to the second remark, and the term involved in the second remark is this term. So we want to estimate K times the Laplacian according to omega phi of capital A. We remember that capital A is the constant delta times capital F plus tau psi minus lambda phi. And so we can write K and move the constant in front of the Laplacian operator. And now we have to apply Laplacian to capital F, which is the second equation of the system of PDEs. So we can, instead of writing Laplacian of capital F, already substitute the result which is given by the system of PDEs. And it is minus small f plus trace according to omega phi of the 1-1 form eta. Now we have plus tau, and we have to apply the Laplacian of phi to the barrier function psi. Okay? And instead of writing just the Laplacian applied to psi, we add and subtract the metric g to it. So we end up with the Laplacian of phi applied to g psi minus the Laplacian of phi applied to the metric g. Now it's more according to the notation, it's more correct to write the Laplacian of trace. Actually, the trace, according to with respect to a metric applied to a function, becomes a Laplacian, but in general, it's a trace. So we added and subtracted a 1-1 form and a tensor, and so it's better to write the Laplacian as a trace, which is the general form of the Laplacian. Now, finally, we have to compute, to estimate this last term, and again we add and subtract the metric, and so we have the trace, which that stands for the Laplacian applied to g phi, which is the trace of a tensor with respect to itself, and minus trace according with respect to omega phi of g again. Okay, very well. Now this minus f can be estimated by the C0, actually the supremum for any time between epsilon and 1 of f, which we always omit the subscript, but in fact f, small f, as many other functions in this estimate, are depending on the time parameter t, and so this is the C0 norm and then the supremum for any t in the interval. Similarly here we can estimate this trace with a similar trick as we did in the first remark, as minus the supremum on the manifold times the time interval of the norm of eta according to the base, to the background metric G, Riemannian G, because this is in the statement of the lemma one of the items we can use for the dependence of the a priori constant. But then we have to multiply this by the trace of according to omega phi of G. Okay? Now we write next to each other the terms where we have this trace of G according to omega phi. Another one is this minus tau trace phi G, and another one is minus minus plus lambda trace. Okay, these are similar terms. Okay, what's left? This is rather delicate, so plus tau times trace, and we can write this trace in this other. This is a metric trace of the matrix inverse of G phi times G psi, because we want to invoke some linear algebra to estimate this term. And the last term here is minus lambda times the trace with respect to phi of G phi. And if we want to write in such a notation this term over here, we have that the inverse times the metric itself is the identity matrix, so the trace of the identity matrix is equal to the dimension of the problem, and so here we have minus those are complex n times n matrices with complex entries, so this term is just an innocent minus lambda times n. Okay, so everything here, let's put some fancy brackets. Everything in these fancy brackets is multiplied by the cutoff function and the constant delta. We put together those kind of terms. This is an innocent term, this is an innocent term, and a little bit of more explanation is needed for this. So this is, I write on the blackboard, is we want to see this as a matrix trace. Matrix okay. let's estimate this term here alone. So we have this. By the algebraic geometric mean inequality, this is so trace divided by n is we can see it as the algebraic mean of the elements in the diagonal. So this is bigger than n times the nth square root of order n of the product of the elements in the diagonal. So we can write k from 1 to n product of phi minus 1 psi psi kk. So the elements in the diagonal. Next, here is needed the combination of the Cholesky decomposition plus the Hadamard inequality. And the combination of those two results together, they say that for a Hermitian matrix positive definite, the product of the elements in the diagonal is bigger or equal than the determinant of the metric itself. So here we can, instead of the product of the elements on the diagonal, we can have the determinant of g phi to the minus 1 times the determinant of g psi. What we gained with this estimate? We gained the fact that the determinant of g psi is prescribed by the structure of the barrier function psi. So, in conclusion, the determinant of g phi is prescribed by the first equation in our system of PDEs. So it is e to the minus capital F times the determinant of the background metric to the minus 1. While this is we saw is a little bit more involved. It was e to the f, there was square root of f, capital F square plus 1 times the volume of the manifold divided by the integral of e to the capital F square root of f square plus 1 according with respect to the volume form of the manifold. So here we have everything is raised to the 1 over nth power. There is some simplification. Sorry. And determinant of G, this is the conformal factor, and I cannot miss the determinant of G. So this is the rewriting of the complex Monge-Ampere equation that gives psi. Okay, so there is another simplification here. Okay, and then we are left with this gadget. This is the most delicate part in the second remark. I leave it on the blackboard for a few seconds for you to copy, and now, for sake of simplicity, we set a bound on lambda. Lambda is a constant to be defined, which can depend on various variables, for example, on the supremum of the norm of eta, and so we want to basically simplify these terms, that each of them multiplies this. So I write above now we set lambda bigger or equal than the supremum of on t times m of the norm of eta plus, so we want also to make it bigger than this tau, which is at most 1, so say plus 10, okay, divided by 2. This is for maquillage reasons, okay, and everything, all of this is basically bigger than 5, so it's positive, there is no problem, and lambda can depend on such a thing, and this is not prescribing the exact value of lambda, but just a lower bound. Okay, so the end of the second remark is that instead of this big bracket here, the square bracket, we can write, we can leave a trace of G with respect to omega phi, and here we can just replace lambda over 2 because of this lower bound just set. Finally, we copy the bound we got here by means of Cholesky and Hadamard decomposition. So here we end up with plus tau times n times square root of f, capital F square plus 1, times d, capital E, d to the minus 1, which is a constant representing this ratio of integrals. We introduced this capital D when we first introduced C. everything raised to the power 1 over n. Okay, so this is the content of I cannot forget plus lambda minus lambda n. Okay, this is the content of remark number 2. So this is the estimate for key that multiplies Laplacian of A. Let me emphasize with squares. This is remark number 2. Okay. Now it's time to insert the result of the remark number 2 above. So we continue. Laplacian phi of key e to the capital A times e to the minus capital A is less or equal than Laplacian phi of key. Okay, now there is another trace again here, and so we want to make them together, to write them close to each other. So from remark number 1 we have minus the supremum on T of the C0 norm of small f times key times delta minus lambda n times key times delta plus tau times n times the square root of capital F squared plus 1 times capital D to the minus 1 over n times key times delta. And then there is this plus trace with respect to omega phi of g that multiplies this minus 10 theta square over 1 minus theta small d square plus lambda over 2. Okay. Now we see that we are basically, the structure of this right hand side is that we make the disappearance of the derivatives of the functions. So here derivatives are not there anymore, the only derivatives are, and this is the content of remark number 3. So the remark number 3 takes into account the Laplacian according to omega phi of key. So at a point with diagonalizing coordinates for the background metric, which becomes the identity, and phi, the second derivatives that are phi kk are delta Kroneker's delta K L bar. This can be written as K from 1 to n of 1 over here, 1 over 1 plus phi k bar times k bar. Okay, so just for intermediate passage, we make use of these diagonal coordinates, but then we will find a more intrinsic result. So these are just instrumental. So this is bigger or equal. We want to take the maximum over over k of this k bar absolute value, and what's left? It's left this is basically the inverse of g phi. So this is the trace with respect to the background metric of g phi. The trace here is the matrix which is the inverse of the identity, which is, by the way, the same guy we already have in the estimates. So this term over here is candidate to go together with these already existing other terms. So the structure looks good. And now the maximum of this, since we are in diagonal coordinates, is bigger than the Hessian with respect to the background metric of the cutoff function, and we can take the norm of it with respect, again, with respect to the background metric. And the trace, everything times the trace. And for the cutoff function, we got estimates for the Hessian in the definition, in the very definition of the cutoff function. So this is bigger than minus 10 theta over the square. This is the estimate for the Hessian in the definition of the cutoff function times this guy over here. So, conclusion, partial conclusion. The three remarks. We only have to add over here minus 10 times theta over d square. And this is the estimates, and of course here we erase this from the remark number 3. We arrive to a form where there are derivatives only on the left hand side. Tomorrow we will start again from this point and continue from here. Thanks for your attention. Have a good day and see you tomorrow.